We are honored to welcome Professor Weiping Zhang, who received the Frontiers of Science Award recently. He will talk about positive scalar manifolds and foliations of them.
Okay, thank you. Thank you for the introduction. Thanks again for the selection committee of this FSA, and also thank the organizers for the invitation. So my talk will be around the scalar curvature, which is the title of this FSA. So I will talk about the positive scalar curvature. So indeed, the positive scalar curvature is a basic invariant of Riemannian manifolds. So then a fundamental question, natural fundamental question, the Riemannian geometry is to study when a smooth closed manifold can carry a Riemannian metric of a positive scalar curvature. And we will see why we study positive and not negative scalar curvature. And moreover, there are roughly two standard methods in studying this kind of problems. One is the minimal surface method pioneered by Zhang and Yao. The other is to use Dirac operators and the Artier-Singer index theory. So in this talk, we will describe some applications of the Dirac operators method, as well as some generalizations to the case of foliations, as mentioned in the FSA. So we start with, to make the talk complete, we start with the concept of scalar curvature. So we take a Riemannian manifold M of dimension n, we let GTM be the metric. So then you take any point P on the manifold and then take any positive number R. We take a ball, we assume R is small, so we take a ball centered at P with radius R. Then we compute this volume. So there is an asymptotic formula when R is small. So this is the volume of this ball on the manifold, and then this is the volume of the standard ball in the Euclidean space with the same with radius and center and the origin. So then when R tends to 0, then there is a asymptotic formula. So it determines for any point determines this number. So then this number is defined for any point. So this is defined the function on the manifold. So it's called the scalar curvature associated to this metric. So this is, in some sense, the weakest invariant associated to the metric is somehow reflects how curved, in some sense, how curved the manifold is. For example, if you take the flat space, Euclidean space, then this one it will be identical to 1. So we get k equal to 0. So on the flat spaces, the scalar curvature is equal to 0. And the function, this number is called scalar curvature at P at the point, and then on the whole manifold, it's a scalar curvature function. The classical result, I think, due to Kastan and Warner, says that when the dimension is larger than or equal to 3, then for any function f with at some point is negative, then there is always a function. There is always a metric such that the stronger result is such that the scalar curvature equal to this function, not only negative. So that it turns out if you have a function has a negative scalar curvature, then in dimension larger or equal to 3, there always exists such a metric. So the interesting question remaining is that what happens if A is positive? It turns out that there are obstructions to this kind of problem. So here the Dirac operator methods come in first. So then I will turn to this Dirac operator, which plays an essential role in one kind of research in this direction. So indeed, if you trace back the Dirac operator, somehow it says that it's a square root of some Laplacian. So indeed, it can be traced back to Hamilton when he invented this quaternion. So in his paper, in one of his papers, he already wrote out this explicit formula where the Laplacian equal the first order operator square equal to the Laplacian, and he claimed that such a formula will be important in mathematics or physics, which turns out to be very correct, because many years later, Dirac in the Lorentzian setting, found this operator here, the gamma I, the polymetrics, and then he found this first order operator square equal to the Lorentzian Laplacian. And this plays an important role in Dirac's theory or in physics. And then many years later, Atiyah and Singer generalized Dirac's construction to curved manifolds, higher dimensional manifolds. They found that it can be well defined on the spin manifold, which is topological constraint restriction condition on the manifold. So many people also call this the operator defined by Atiyah-Singer called Atiyah-Singer operator. But Atiyah and the Singer themselves call this a Dirac operator. So we also call this, follow the Atiyah-Singer's terminology, call this Dirac operator. So now we go to see what is exactly how to define the Dirac operator. We take an even dimensional manifold. We assume, for example, for its closed, it's a Riemannian manifold, it's a metric GTM, and we assume it is a spin manifold. That means it's a topological, verifies a topological condition for the second Stiefel-Hoenig class equal to 0 of the tangent boundary equal to 0. So we also then with the metric we have a similar connection and the associated curvature. So the spin condition and the metric determines the bundle of spinors, which is an emission vector bundle. On the even dimensional manifold, it admits a splitting. Z2 graded splitting S spinor bundle equal to the S plus negative positive spinor bundle and negative spinor bundle. It also carries induced emission metric and also a connection, emission connection. And also for more general, if we can also twist it with an arbitrary emission vector bundle. So if we have an emission vector bundle with this emission metric E, and we take an emission connection, which means preserve this emission metric, then we can define this following Atiyah-Singer, the Dirac operator defined in this way. So if E is a trivial complex bundle, line bundle, then we just denote it by D. So this is the Clifford action acting on this spinor bundle, and EI is a local orthonormal basis. And the sum, this connection is induced on this tensor product connection. So so this sum does not depend on the choice of local coordinate, local orthonormal basis. So it is well defined. So it is a globally defined operator. So in even dimension, we restrict the D plus acting on the plus bundle and D minus acting on the minus bundle. Then it is the total D with this assumption will be self-adjoint. So the adjoint of DE plus will be equal to DE minus. In this way, we can define the index, this elliptic operator on the closed manifold. So the kernel of D is of finite dimension. So we can define this index with the difference of this dimension of D plus minus the dimension of D minus. And this turns out does not depend on the metric and the connections involved in the definition. So the famous Atiyah-Singer index term says that this analytically defined index, which is topological, which does not depend on metric, indeed has a topological, explicit topological expression, and in the Chen-Wei form, with our curvature defined, connection defined, it can be written in this way. This is the A-hat form. It's a Hertzsprung defining Hertzsprung A-hat class. And this is the Chen character form, define the Chen character of the twisted bundle E. And here I will remark that the spin condition is essential. For example, for CP2, the A-hat genus, A-hat genus is minus 1/8, is not an integer. And while tautologically for this index, it should be integer. So the spin condition turns out essential. And an early application applied of this Atiyah-Singer index term is indeed applied to the scalar curvature problem. So that Lishnowitz compute explicitly the square of the Dirac operator. He found that it's equal for the Bourgeois-Laplacian plus the scalar curvature over 4. Here, the Bourgeois-Laplacian is the negative and here, of course, is the scalar curvature of the metric. And with this, the Lichtenau says that if on a closed spin manifold, if there is a metric of positive scalar curvature, then the heterogeneous equal to 0. And the proof is indeed a one line. So because this scalar curvature is positive, so then with using this Lichtenau's formula, the d square will be positive because this Bourgeois-Laplacian is negative. And then the kernel of d will be 0. But by the single index theorem, the difference of some kernel equal to the heterogeneous. So then you see that the index should be 0 and the heterogeneous should also be 0. So this is the simple applications and of this single index theorem. It's dating to 1963, and this gives the first non-trivial obstruction in the high dimension case. That there are a lot of examples of spin manifold with heterogeneous non-zero. So on this manifold, there will be no metric of positive scalar curvature. So then there will be a lot of people study this basic question. So the next result I will mention is that Gromov-Lawson in 1980s, around in the beginning of 1980s, proves that for every simply connected non-spin closed manifold of dimension larger or equal to 5, indeed carries a metric of positive scalar curvature. And on the end of spin manifold, there are obstructions. And many years later, Stolz solved Gromov-Lawson's conjecture, saying that stated that if you have a simply connected spin manifold of dimension larger or equal to 5, if it carry, then the manifold carries a metric of positive scalar curvature, if and only if the so-called Thiele-Milnor singles alpha invariant equal to 0. And in dimension 4K, for simplicity, I will just concentrate on heterogeneous. In dimension 4K, it is indeed that this alpha invariant is indeed heterogeneous. So it says that, for example, the corollary is that consequence is that this question, whether a manifold carries a metric of positive scalar curvature, has a satisfying answer if for simply connected manifold of dimension larger than or equal to 5. If it is non-spin, then Gromov-Lawson says it always there exists such a metric. And if it is spin, then Stolz gives the equivalence condition. In dimension 4K, it means that if and only if this heterogeneous gives a sufficient and necessary condition. So this is for simply connected manifold. So what's about your natural question? What's about non-simply connected manifold? The simplest case for non-simply connected manifold is torus. Then Xiong-Yao and Gromov-Lawson proved that in around 1980, proved that there is no metric of positive scalar curvature on any torus. And Xiong-Yao's method is using minimal surface or minimal hypersurface. I say it worked for dimension less than or equal to 7 at that time. And Gromov-Lawson make use of Dirac operators. And in many cases, it turns out that the deformed Dirac operators can also play an important role in deformations of Dirac operators. And the setting is indeed very simple. So instead of consider a single twisted vector bundle, we consider a Z2 graded vector bundle. It's a direct sum of two emission vector bundles. And we take Z2 graded emission connection, certainly. And then we assume, for simplicity, we assume that it's an even dimension spin manifold. And we also assume there is a V, a self-adjoint order isomorphism of Xi. The order means that it exchanges Xi plus and Xi minus. And in this case, we can consider the tensor, the Z2 graded tensor product of this one. That means it admits a natural Z2 splitting, which the plus part will be the S plus tensor with Xi plus and plus S minus tensor Xi minus. And then the negative part will be S minus tensor Xi plus plus S plus tensor sign minus. And the Dirac operator, the positive part and negative part, the natural splitting, the D plus will be mapped from this the plus part of the super tensor product or Z2 graded tensor product to the negative part. And then since V is self-adjoint, D of course is self-adjoint. So any real number, we can make a deformation, dt equal to D plus TV. This is also self-adjoint operate. If you compute the square, so this square tautologically equal to this way. And here the bracket is the Z2 graded bracket with respect to Z2 splitting. It's not the it is a d psi v plus v d psi, not the d v minus v d, not the usual one. Here with this setting, it is naturally says that this bracket is zero of zeroth order. This is the key point in this aspect. So now we are still, of course, in compact manifold, closed manifold, it gives not essentially new immediately. But for non-compact manifold, if we assume that it's a complete magic, complete non-compact magic, then we assume that the V, the endomorphism V, is invertible outside compact subset. And moreover, we assume that the norm of this V has a positive lower bound outside the compact subset. And moreover, we assume this V outside the compact subset identify these two bundles near infinity, the outside the compact set near infinity. That we assume this one, we write the condition in this way. Then if you see that under this condition, the middle term would be equal to 0. So when the middle term equal to 0, the dt square would have a uniform lower positive bound near infinity. In this case, one can show that the kernel of this dimension is finite dimension, just like in the smooth compact case. And in this case, it carries an index which can be computed in the right-hand side. It's called this relative index theorem. And here, since these two bundles are identical near infinity, so the difference is 0 outside the compact subset. So the right-hand side, the integration is on a compact subset, so it is meaningful. So the name of this relative index theorem indeed is inspired by the original relative index theorem of Gromov and Lawson. So originally, Gromov and Lawson assumes that the scalar curvature has a uniform positive lower bound outside the compact subset, and psi plus or minus are both trivial bundle. So then, in this case, we can write near infinity. We can write this d square by using Lichnow's formula. We can write this as a Buchner Laplacian, which is negative plus scalar curvature. So near infinity, if this scalar curvature has a positive lower bound, we have this formula. And then we can, in the right-hand side, we can make move t tend to 0. So it still has a uniform positive lower bound near outside the compact set near infinity. So we can still have this finite dimensionality of the kernel. And then, since the index does not depend on the continuous family of spread operators, so we can compute this index when t equal to 0 and applying the previous relative index, we get the difference of this index, because this scalar curvature assumption, the individual index is also well defined. The difference of these two index equal to the right-hand side, which is the same topological interpretation as the relative index theorem. So this is Gromov and Lawson's relative index theorem. They assume that the scalar curvature has a uniform positive lower bound near infinity. And this theorem, indeed, in their famous paper, has a lot of important applications. A typical applications applies to the so-called so-called enlargeable manifold or area enlargeable manifold. The definition is as follows. So we just record the definition. So we give a Riemannian manifold of dimension n. Then it is called area enlargeable if for any small epsilon there is a covering, a Galois covering pi for m epsilon hat to m with the lifted metric, and a smooth map, and a smooth f from this covering space to the unit sphere of the same dimension, which is constant near infinity. That means outside the compact subset, the image of f is constant, is a point. N of non-zero degree is non-zero degree. And that for any two form alpha on the sphere, the pullback form with respect to the lifted metric, the norm is less than equal to, is dominated by the epsilon of this norm of alpha on the sphere. And if M is compact, of course, we can change epsilon. This definition does not depend on the GTM. But for non-compact manifold, it is a concept associated to the metric. And a typical example is that for the circle, for example, for the circle S1, you can always enlarge, take a covering, nth covering to it, map it in a contraction, and this will be the F would verify this. So circle is taught, so enlarge suddenly means enlarge into a very large. So this circle is clearly such an example. And so of course, then the product of circles, torus, is also enlargeable, verifies this condition. And also that if you have enlargeable area enlargeable manifold, then the connection with any other closed manifold of the same dimension is also area enlargeable. Then the famous theorem of Gromov-Rosen says that if you have a complete area enlargeable spin, assume spin, because if we use Dirac operator, we always assume spin area enlargeable manifold, then the scalar curvature of the metric cannot have a positive lower bound. That means the infinite of Ktm will be less than or equal to 0. So the proof is indeed very simple. So let me outline just the 2 slides. So we recall that the area enlargeable condition means that there is such a map for any epsilon, there's a map from covering space to the standard unit sphere. So we take on the unit sphere, we assume simply assume n is even. Then there is a emission vector bundle such that the Chern character of E is non-zero evaluated on the sphere. Then we pull back this bundle using this map. We pull back this bundle to the covering space. Then on the covering space, we consider this twisted Dirac operator. Then by the Lichten's formula, the square of the equal to Bochner Laplacian plus the scalar curvature, which is a pullback the scalar curvature, and plus a term involving the curvature term involving the twisted bundle. Then since that we have an area enlargeable condition. So for any U epsilon, this curvature term will be equal to pullback the curvature term. The curvature is 2 form. So the curvature 2 form, the pullback is there's the O epsilon term here. So where epsilon small, this term is very small. So if we assume the scalar curvature has a uniform positive lower bound, then using this one, when epsilon very small, you get a positive number, positive operator here. The kernel will be 0. So the relative index will be 0. The relative index will be 0. So this kernel will be 0. Then the trivial coefficient, you can apply the same trick. Then you make it the difference of this index, which by the Gromov-Rosen's relative index theorem is equal to this one. But this one, if you compute directly, it is indeed equal to the degree of this map f and the Chern character. And we have assumed that Chern character equal to 0. And in the definition of the enlargeability, we assume the map is f is of non-zero degree. So then we get a contradiction because this far right-hand side is non-zero. So that means if you cannot assume this is curvature, scalar curvature has a uniform positive lower bound. So this gives a very simple proof of this factor of this Gromov-Lawson's theorem. Of course, in the compact set, if M is small, is compact, then this one means that there's no positive scalar curvature on the area enlargeable manifold. And indeed, this is since torus is enlargeable, area enlargeable. So this goes back to the Xiong-Yao and Gromov-Lawson. This gives a proof. This gives a proof that there's no metric of positive scalar curvature on any torus. Moreover, since the torus connects sum with the manifold is also area enlargeable, so the consequence is that if the manifold there's no metric of positive scalar curvature on any such that connects sum if manifold is spin. If the manifold is spin. So this kind of result is interesting because many years later, Lecomte make an important insight, says that such a property that the no metric of positive scalar curvature on the connection with torus indeed implies the positive mass theorem for the closed manifold N. For the closed manifold N. Now let us recall that indeed for positive mass theorem it was first proved by Xiong-Yao in dimension less than or equal to 7 using minimal hypersurface method. And then Witten proved that the positive mass theorem holds for any closed spin manifold. And Xiong-Yao more recently presented proof that the positive mass theorem is verified for all closed manifold N by using minimal hypersurface method. And indeed, what they prove is that they prove that this connected sum does not have a magical positive scalar curvature for any manifold N. And then they using Lecomte's criterion, they get the positive mass theorem. And then for a long time, the embarrassing for Dirac operator people that there's no Dirac operator proof even for any non-spin N. So the long-standing question, even for T4 plus a connect sum with CP2, so these questions already appear in Gromov-Lawson's original paper. We try to go back to this later. And then another naive question is that back to Gromov-Lawson's result, they say that on a complete spin area enlargeable manifold, then the scalar curvature cannot have a positive lower bound. But in our previous relative string index, we have generalized relative index theorem, which holds with assumption on V, not on the uniform positivity of the scalar curvature. So it's a naive question whether one can replace this inequality by this stronger inequality. And so far, there's no general result available. But in the special case of connect sum, on that sum, recently we can show that if M is a closed spin area enlargeable manifold, and N is a non-compact spin manifold, then there is no complete metric of positive scalar curvature on the connect sum. So as a corollary, if M you take a torus, then that means the torus connect sum with any non-compact spin manifold cannot carry a metric of positive scalar curvature. So it is easy to show that such a manifold does not carry a metric of uniformly positive scalar curvature. But here we replace that by the positive scalar curvature of complete metric. Indeed, such a result has some recent interest because when n equal to 3, this corollary is due to Lesson, Unger, and Yao, a recent result. And then when n is dimension is between 3 and 7, it was also proved by Chodoshi and Chao Li in a recent paper without assuming n is spin. They use mu bubble and the minimal hypersurface method works for any manifold. And of course, such kind of statement is closely related to the post-mass theorem in the non-compact setting. And for general non-spin, the case is still open for higher dimensions. So now now let me do some. Let's go back to the following remark, previous remark about this higher dimensional post-match theorem for non-spin case. So then the general non-spin case is very difficult. So we now concentrate only on the spin C manifold. So spin C manifold is a slightly generalized version of the spin manifold. So that means there is, by definition, for spin C manifold, if and only if there is a complex line bundle such that the first Chern class of this is equal to the second stable Quinn class. So when L is a trivial bundle, then W2 equal to 0. This is a spin manifold. So on the spin C manifold, you take a line, you view this line bundle as a Euclidean rank 2 vector bundle. You can always take a transversal section X. Then the transversal section, the zero set of this transversal section will be a co-dimension 2 smooth closed manifold, closed submanifold. Then we also using this Z2. We also assume on total manifold there is a Z2, a graded emission vector bundle with the Z2 splitting. Then we also assume there is an odd endomorphism of Z2 graded bundle, such that odd means V exchanges psi plus and minus. And we assume this V is invertible on this submanifold, Then we assume that there's a metric such that the scalar curvature verifies this one, verifies this condition. Then we say that we state a theorem says that under this kind of assumptions, which is V is invertible under this submanifold with this curvature condition, then the spin C index, which is topologically expressed in this term, will be 0. Here the Chern character is the Z2 graded Chern character. There's a difference than here. So if we have a spin manifold, then the line bundle is trivial. Then the X you can take nowhere 0. So you can take this sigma, the submanifold is trivial, and the psi you can take just a trivial line bundle. This A hat genus equal to 0. So this one generalize, in some sense, Lichtenau's theorem to the spin C setting, And this is the first sentence. And such a theorem that's interesting that it's correlates that if M is a closed spin area enlargeable manifold and N is any closed spin C manifold, then the connection will not have a metrical positive curvature. A corollary of this above theorem applies this setting. So if you take this spin manifold as a torus, you recover Shung-Yao's result for spin C manifold. And it gives, for example, this index theoretic proof of this result for spin C manifold. And also, because area enlargeable covers a lot of other manifold, for example, for the hyperbolic manifold, is also area enlargeable, closed hyperbolic manifold. This is a kind of result for higher dimensions. This connection cannot carry the metric positive scalar curvature. And then we give an outline of this one. So on the spin C manifold, instead of a usual Dirac operator, we have a spin C Dirac operator, which maps the spin C bundle of spin C spinors and tensor with this Xi, this tensor product Xi. And the spin C spinor bundle can be written in this way. Both STM and the square root of L is in general not well defined, but their tensor product locally can be extended to a globally well-defined bundle. This is totally bundle. Then if you compute the Lichtenau's formula of this term, then there's an extra term here arising from this line bundle. And by our assumption, these two terms is positive. So if we have no red term, we can apply the index equal to 0. We can apply. So this red term will cause some trouble. But here the simple observation is that the submanifold indeed is an obstruction to the M being spin. So you cut off the spin manifold, cut off this sigma, then the M minus sigma is a spin manifold. Moreover, the line bundle restricted to to this one, the cutoff, this sigma is a trivial bundle. So outside this small neighborhood of this trivial, you can take L to be a trivial bundle, and you can take the Dirac operator. Naively, you can apply the Dirac operator method. So then everything was in some sense localized. The problem will be localized to the submanifold. Now here we will use deformations of Dirac operator. You can to prove this one. Of course, this assumes that the sigma is smooth. The general case for sigma is non-smooth is still open. We don't know how to do it yet. So finally, we come to the foliation case because this is mentioned in the FASA. So we have duty to report something related to the foliation. So a foliation, by definition, is that you take F as subbundle of the tangent bundle of a smooth manifold. Then we call F integrable. Integrable if for any section, two sections of this subbundle, the Lie bracket is still a section of this bundle. Then, with this condition, you can apply the Frobenius integrability theorem to say that for any P in the manifold, there is a submanifold called this FP passing through this point such that F restricted to this submanifold is indeed the tangent bundle of this submanifold. And we call that this MF is a foliation, and M is foliated by this submanifold called leaves, called this FP submanifold. So the simplest case is the fibration case. It is the fibration case. So if you have a fibration case pi, then this vertical bundle Tm would be pi star of Tb horizontal lift plus the vertical bundle. This is tautologically integrable. This is so foliation is a far-reaching generalization of the fibration case. And Kohn proved a generalization of this famous Lichtenau theorem we have recalled in the very beginning of this talk. He proved a generalization of this Lichtenau theorem to the foliations. So his theorem says that if you have a closed oriented foliation such that the integral subbundle F is spin, that means in the fibration case, that means the vertical bundle, tangent bundle is spin. Then if there is a metric on the total manifold such that the restriction on each leaf, on each submanifold FP has a positive scalar curvature, then the heterogeneous of the total manifold would be equal to zero. Of course, when F is the total tangent bundle, then this is just the Lichtenau theorem. So the one point of the difficulty is that here the total manifold need not assume to be spin. So you have no Dirac operator on the manifold naively. So even in the fibration case, even in the fibration case, each fiber is spin, and the total manifold need not spin. So in this case, in the fibration case, in the simplest fibration case, the Kohn theorem is the corollary of this family attaching the index theorem. The family attach index theorem. So then Kohn wants to generalize this family attach index theorem to the case of foliations. So he developed a big machinery. So Kohn's proof using the cyclic homology in non-commutative geometry, and also the Kohn-Scarndalis longitudinal index theorem, which is a generalization of the attaching families index theorem to the case of foliations. So then for geometers, its natural question is that the Kohn theorem, one can prove Kohn theorem by using a direct geometric method. And indeed, I think this is a question first proposed to Ke-Feng Liu by Professor Yao. But Ke-Feng Liu was was by then a student at Harvard of Professor Yao. And then later when he visited the Nankai Institute, he challenged us. So what we do in the first case, what we do is that we construct what we call the sub-Dirac operator. That means if you have so we write this, if you have a manifold Tm equal to E plus F plus F, the orthogonal with this can be identified with this one. If we assume only this is spin, so instead the total manifold is not spin, we can consider the bundle of spinor bundle, then tensor with the exterior algebra of this normal bundle. When we work Dirac, this is locally a Dirac operator, because in general case, if you have a right even, if we assume that this normal bundle is even, we have this one, and this two is STM. Tautologically, locally, just like in the spin C case, locally you can still use Dirac operator, but globally we only assume F is spin to recover this result. So then with this we can prove Cohn's theorem. For example, Cohn's theorem for this easy fibration case, we can without using a family index theorem. And we try to generalize this strategy to the more general setting. But the Cohn's proof there's other difficult geometric difficulties. So we do not require, because the time is not allowed. But we need to apply to a more sophisticated situation. So finally, we can indeed get a geometric proof of Cohn's result. And indeed, in the process, we arrive at a similar result that alternating generalization of Cohn's theorem, a generalization of Lichter's theorem. So we now assume a foliation. Instead of assume F is spin, we assume the closed manifold, the total manifold is spin, is a foliation. Then we make the same assumption that there is a metric on the tangent bundle such that its restriction to each leaf have a positive scalar curvature. Then the A hat genus equal to 0. So here the A hat genus is the index of the Dirac operator. So indeed our theorem applies to more for any dimension. That if you apply it for any dimension, it's alpha m equal to 0. But for dimension 4k, if we consider the A hat genus, so we arrive at the same conclusion of Cohn's result, but slightly change the definition, the condition on the spin condition. And as a corollary, you can show that on the torus there's no foliation of positive Levi scalar curvature. That means if you have F is you have an integral subbundle of a torus, then there's no metric on the torus such that when restrict to each leaf has a positive scalar curvature. So when F is the total tangent bundle of torus, this recovers generalized theorem, recovers the theorem, original theorem of Sheng-Yao and Gromov and Lawson. And more recently, we can prove also a generalization of Gromov-Lawson's original result for the enlargeable manifold to the case of enlargeable foliations. So we're not stated in detail, but we can, many theorems, classical theorems can be generalized to the foliations in this sense. And finally, let me mention that there's a natural open question in the foliation theory, is that if you have a foliated manifold, and if there is a metric on the tangent bundle such that the restriction on each leaf has positive scalar curvature, then the question is asked whether there is a metric on the total manifold such that has a positive scalar curvature. So this is still open. In the simply connected, if the manifold is simply connected, combine our theorem with Stowe's theorem, we can give such a positive answer for the simply connected manifold of dimension larger than or equal to 5. But in general, it is still open. It's a natural question It's open for a long time. And finally, at last, I will be mentioning that recently, Gromov paid a lot of attention to the questions around the scalar curvature. Recently, he wrote more than 500 pages survey called 4 Lectures on Scalar Curvature. It contains all of the kinds of questions concerning the scalar curvature and so on. So this will be a rich source for anyone who will be interested in this kind of problems. It involves both minimal surface method and the scalar curvature method. So for time's sake, I will stop here. Thank you very much.
This open question.
Yeah,
If you take the metric on M
yeah,
and multiply its restriction to each leaf by
yeah,
a small constant,
yeah.
that doesn't work.
Does not work because 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 then you have no way to come back to this manifold. Because if you have on the product, you may construct a lot of metric upward scale curvature, and if you multiply small manifold, but if this property cannot go down to the original manifold easily. Yeah, 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 yes, yes. For the adiabatic limit, it does not work. For the vibration case, it works. For the foliations, there are obstructions. This is the main difficulty for Cohn's theorem. Even for Cohn's theorem, for this kind of problem. So in the vibration case, you can take adiabatic limit to make the scalar curvature positive. So you get very easily the result. The generalization of this situation is called Riemannian foliation. Riemannian foliation. So that means the normal boundary, there is a bot connection. It's a leafwise connection, leafwise flat connection and bot connection. If the bot connect on the normal boundary, there's a connection, leafwise flat connection, preserve the metric, then everything works. Adiabatic limit trick works. But there are obstructions to this. Yeah, thank you.
I'm wondering whether we see a theorem for Yarou's theorem or Faulkner's theorem approach.
I think for Larousse theorem, it works. But if you need some modified assumptions, yeah, it's not hard to do this. In the closed case, in the non-compact case, you still need something to do, because if in the non-compact case, if this sigma is in the interior, then you can do it. If it is intersection with the boundary, then something you need to do manifold corners may be more difficult.
Okay, let's thank the speaker again.